The goal of the DARPA Robotics Challenge is to generate groundbreaking research and development so that robots can perform the most hazardous activities in future disaster response operations in tandem with human counterparts. Achieving this goal requires significant advances in robotic hardware and software. The first event of DARPA's Robotics Challenge is the Virtual Robotics Challenge, or VRC. The VRC is a cloud-based competition designed to test software teams' abilities in robot perception, manipulation, and locomotion in a virtual environment through simulation of a robot. From 126 originally registered teams, there are now only 26 from 8 countries that have qualified to participate in the challenge. These teams are all vying to be one of potentially 6 that will be given an Atlas robot to be used during DARPA's robotic demonstration events in 2013 and 2014. DARPA's simulator accurately models real-world physics and behaviors, including direct interaction with the robot, its sensors, and the virtual world. A critical component of the VRC is to simulate people and robots collaborating over a degraded communications channel, as often happens in disaster scenarios. The competition will enforce a round-trip latency of 500 milliseconds and will vary the number of communication bits from run to run, from a high of 900 megabits to a low of 60 megabits. This simulated environment provides a level playing field for teams to work within. The virtual challenge has 3 simulated tasks that are ranked by task completion amount of data exchanged between operator and robot, and task completion time. Task 1 involves the robot walking to and then entering a small utility vehicle. The robot must then drive the utility vehicle across a course that is modeled after a basic suburban area using the vehicle's steering wheel and pedals. Spaced along the road are obstacles that must be avoided, as well as scoring gates that must be driven through. This task not only tests the performer's ability to simultaneously control multiple limbs of the robot at high speed and vision-based planning to avoid obstacles, it also pushes performers to show the dexterity of their control by having the robot climb into the vehicle and position it for a controlled drive. The task is considered complete when both the vehicle passes through its final gate and the robot exits and walks to its own final gate. Task 2 is a walking challenge over various types of terrain that the robot may have to traverse in the real world, testing foot placement and body control. Initially, the walking surface is simple pavement. This pavement gives way to a simulated mud pit which generates a mild slipping hazard, and which will require more thoughtful foot placement and body control. Again, there are several scoring gates that must be passed through, guiding the direction of the robot within the course. Finally, the teams must cross a rubble pile full of uneven surfaces and trip hazards. Some of the objects in this pile are free to move, so the teams must make a choice to either plan their footfalls with high precision to avoid the obstacles, or adjust quickly to shifting weight and altered states of balance while stepping on obstacles. The main goal of this task is to demonstrate the various levels of control the performers have developed, allowing them the opportunity to change walking behaviors on the fly to optimize overall speed. Task 3 focuses on manipulation. The goal is to walk to a table with a fire hose on it, pick up the hose, and securely attach it to a pipe mounted on a wall. Attachment comes via a collar on the hose that must be screwed onto the attachment point. Once attached, teams must use the robot to open a nearby valve, which in the real world would allow water to flow into the hose. Given that the hose is not a rigid object, it can be difficult for the robot to grab and handle. Additionally, elements of this task will require fine motor skills, two-handed synchronized manipulation, and good hand-eye coordination.